Okay, finally we will see something. Excellent. I mean, sorry for the delay, OBS decided to upgrade. So, welcome to this new lesson of probabilistic robotics. This round we will, exactly, let's wait. I have just one concurrent viewer now. Two, three. As always, at 10 we start. Seven. Getting there. Still 7. Come on. 3 more. No more than 7. 8. 10. All right. So welcome to this new lesson of probabilistic robotics. Topic of today will be RANSAC and an extension to multiple sensors of ICP. So like what we could do if we want to register the position of multiple devices that are observing the same set of points in the world. So let's start with RANSAC. And prior to that, I would like to recap what we have done in the previous lesson, where we just gave a very quick and dirty course or dirty recap of computer vision. And at the end of that lesson, it should be clear or understandable at least how it is possible to determine the relative transformation between two cameras up to a scale, given that we assume that these two cameras observe a set of points in the world and the same set of points in the world, or substantial. They have a substantial overlap. The two views have a substantial overlap. Having this, we could imagine basically to run a feature detector / descriptor on the two images. This feature detector will first find based on some heuristic, some salient points in the image, which are the so-called interest points, which are typically characterized by image regions where we have a high variance in the gradient or in the direction of the gradient. So like special points like the corners, the intersects of lines and these sort of things are typically resulting in points that can be easily distinguished between similar images or between images of the same scene, which are taken at small difference of viewpoint. Once we have this, a classical computer vision pipeline would take all these points, which are just pixel coordinates in the image, and for each of them they will try to extract a description of this point, which is invariant to rotation, translation, like to extract a description of the point that doesn't change much if we observe this point a little bit further or a little bit closer. Clearly, this description, which we could imagine as a vector, is a vector in multidimensional space that is a function of the neighborhood of the image around the interest point or where we extracted that we extracted at the previous step. So the pipeline works as follows: I give you an image, you choose based on some algorithm some points which are cool not many, just a few of them, and for each of these points you take a small patch of image around it and you compute a so-called descriptor of this point. In a simplistic way, you could also think as the descriptor of this point as if it was a mini image attached, the mini image patch centered around that point. Once I give you this, I do this process for every image, or let's say for 2 at the beginning. What I have left is a set of points intended as UV coordinates on the image and a set of descriptors, which is image patches, just to make it simple, or vectors. Then, in order to figure out which point is which, it's quite common to run a comparison between the 2 set of points. So you take the first, the descriptor of the first, that encodes its appearance, and then you compare it with all others, with the descriptors of all other points in the second image. And you find, if you find a close match, then you say, okay, this point and this point, they are presumably originated from the same element of the word. And you form a correspondence. And then you do the same for the second point, the third point, and the fourth point. Clearly, there is a lot of black magic and heuristics involved in this process. First of all, the extraction of the interest points. Second, the calculation of a feature descriptor that even if it is designed to be invariant with respect to rotation translation, this invariancy holds only up to a limited bound. And in the end, what happens is also that several elements in the image might look alike, like just imagine a checkerboard, where all corners of a checkerboard, if looked in a narrow way, they look the same, right? And in this case, our descriptor matching will get crazy if we use just this naive strategy. Anyway, we could imagine that we have a bunch of matches between the point of the 2 images, and then we want to respond to the question, where am I with respect to before, right? So up to a scale. So what we could do is to take these correspondences, calculate, as I was mentioning last time, the essential matrix, then out of the essential matrix we could extract the transformation, and we could be happy. The problem is with this schema is that typically the number of good correspondences obtained by this heuristic are a small fraction of the total number of correspondences that is returned. Let's say 20%. And with 20%, well, there's no robust kernel, there's nothing that holds in order to figure out a reasonable solution. And so we have to invent a way to be able to initialize or to determine this transformation even with this high percentage of what we call outliers or wrong correspondences. Clearly, this schema or this problem might arise not only in the case of vision, but also in other circumstances. For instance, if you have 2D landmarks, right, and then you see these landmarks in a certain configuration, and then you want to relocalize based on this set of landmarks. But you don't have a clue on where you were before, so you want to do an initial alignment, but still, if you don't have good correspondences at the beginning, our schemas that we have used so far do not really work. Okay, so we have to invent a way, or to not invent, to present a way that will allow us to determine a reasonable registration or a satisfactory set of satisfactory parameters given a set of data with high percentage of outliers. And this is RANSAC. Now, to make the example streamlined with what we have been talking about, let's say the last 20 days, I will talk about 3D point registration. And because it's the easiest problem to visualize, but clearly could be any registration problems where you have correspondences involved. For simplicity, let's just think about, we want to register a set of 3D points. Unfortunately, in this circumstance, we assume that we do not have neither a reasonable initial guess nor a set of decent correspondences, or let's say we have no correspondences at all. And then the question is like, how could we carry on this registration? Well, any idea? Well, if you considering the latency, you write down the ideas, and then I will read the answer later. So our task is as usual. We want to find a transformation that minimizes the distance between corresponding points. We don't have correspondences, but between points that minimizes the distance between nearby points after the transformation. We could define this problem this way. Okay? So an idea to approach this problem is to use the typical wishful thinking. Now, the wishful thinking means, okay, this problem is too complicated to be solved as it is presented, because I have 2 point clouds and I don't have any correspondence that tells me what it is what, and I don't know really how to register them. I mean, okay, if we want to be really computationally brute, we could just try all possible rotations and translations, like in a grid-like fashion, and then we will do this 6D search, and after half a day we will manage to find some sort of alignment. But let's forget about these things which are too slow, and let's think how this problem could become easier. Well, it could become easier if we knew a minimal set of correspondences. So I don't need to know the correspondences of the whole point cloud, like between each element. I just need to know a minimal number of decent correspondences. How minimal? Minimal enough that will allow me to determine the relative transformation between the two, because otherwise there's nothing I can do. So if I give you not all the correspondences, but just a minimal set, minimal, how many correspondences do I need in order to find a solution for this 3D registration problem? This is a question. If I know this minimal set, we could just like use this minimal set to calculate a solution. Once we have calculated the solution, basically by registering these points here, of which we assume we know the correspondences, we could determine a solution. But this solution is then applied to all other points in the set. So I could just take all other points and put them according to the solution. This will automatically make the points which are closer, or the pairs which are closer, in reality, closer also under my solution, like this figure here. So I could determine, clearly I'm using only 3 correspondences, so I won't be that accurate. Okay, I've given you the answer. For determining a solution over the registration of the points in 3D, 3 points are sufficient. I mean, it's quite easy to also to imagine, because 1 point constrains me along in this way, 2 points constrain me this way, and the 3rd point locks me. So you could determine the solution, and then you could basically identify for each point which one is the closest in the other set. And you call this closest an inlier. Or if you have some correspondence finding heuristic that comes from the appearance or whatever, you could just decide to validate or not a potential link between corresponding points. And then what will happen is that some of these points will fall close after computing the solution. Some other points will not, like for instance this pool one here. And then we can count the good points and we call them inliers, and we could drop the bad point. Once we have this identified, based on this initial set of 3 correspondences, a potential solution, then we could identify the inliers, and then finally we could use a traditional solver that we feed with the proper initial guess and with the inliers that have been revealed at the previous step to refine this final solution. In doing this step, it is common to to ignore all the correspondences, all the matches which have been reported to be false matches, thus outliers, after applying the initial solution. Okay? This holds for registration but of 3D points. In case of images, well, you could run the very same procedure, only that the minimal set, instead of being consisting only of 3 points, consists of 8 points, because we have seen that the 8-point algorithm is called this way because it requires 8 points to compute the solution. Okay, so you will need, in this case, 8 decent correspondences to bootstrap your system. Okay, then the sad truth is that we do not have a way to select pairs of points. We do not have a way to select among this potential set of correspondences typically the good one. We just have out of our system, shall it be an appearance-based system, or if we don't know anything, our set of correspondences consists of all possible correspondences in the set. So n times m correspondences, if we don't know anything. We don't have a way to determine a decent set of correspondences. So what we do is a sampling approach. So we say, okay, you know what? Given that I don't know which one is this minimal set of correspondences or pairs, I will just proceed as follows. Given one round, I give it a try. I pick up 3 or n correspondences, n minimal, n with n is the minimal number of correspondences from this big set. I get these correspondences. I pick them at random. I get these correspondences and then I compute the solution. I can compute the solution, I can determine the inliers, I can determine the outliers, and then I might say, okay, you know what, this solution is a good solution or is better than another solution that I have found before if the number of inliers that I find with this solution calculated from the minimal set that I have sampled has a higher number of inliers than the one I've sampled at the previous round. So you repeat this schema over and over, and each time you pick the best, you keep the best solution. At the end of the game, you will have the best solution so far, so which is the solution with the most inliers. And once you have this, you typically run a final registration by only using the inliers to determine the final alignment. Okay? Clearly, it's am I guaranteed that it will work? No, I'm not. There's some randomness in here. As a consequence, the probability of success of RANSAC will be dominated by some factors. One factor is clearly the number of inliers, or the number of good correspondences that you have in the initial set. Because if you have only good correspondences, then, well, in one go you will be done, depending still on the noise, but still. And it also be influenced by how large is the minimal set. Because if I just need to pick 3 good correspondences, well, this is much more likely than picking 8 good correspondences. So, an important game of RANSAC, especially when I give exercises, is not to consider it the RANSAC algorithm. It's just a schema. It's just a template where you put in or that you adapt to address the specific problem. To implement this schema algorithmically, we need the following things. First of all, we need a procedure that can select the correspondences. In our vision case, this procedure was the comparison of descriptors, or maybe another procedure. But I need a piece of algorithm that, given these two entities, shoots a potential set of matches. This and this match, this point and this point match, and so on. Clearly, the more accurate it will be, the lower will be my outlier ratio, so the higher will be the inlier ratio, and presumably I will manage to find the correct solution in less rounds, or actually to find a solution. Then I need also a procedure. Then once I have this correspondence set, I also need a procedure that picks from the set of correspondences that have been shoot at the previous step a set of candidate correspondences to compute my minimal solution. In the worst of the cases, I can just like pick them at random. So I have this set of matches, and I say this, like with closed eyes, and then I try it. But sometimes I could exploit some invariant of the data that I am analyzing. For instance, in the case of a point cloud, where if I want to register sets of 3D points, I might observe that one invariant in this space is the distance between 2 points within the same cloud. Okay, so it would make sense when I select a set of correspondences to pick a set of 3 correspondences in the one cloud and 3 points or 3 correspondences in the other cloud that was the distance between each other is more or less alike, because if on the one side I have a triangle which is like that, and on the other side I have a triangle which is like that, those two will never align. Okay, so you could use some sort of invariant, but in the worst of the cases you go uniform. Another ingredient that I need to implement this schema is clearly a minimal solver that has to be immune to the initial guess, because when I do the initial registration, I do not know where these two objects are, and I would like to determine the solution in any circumstance. So better if it is immune to the initial guess. Finally, the last thing that I need to implement RANSAC on a problem is a procedure to count the inliers. Like, okay, now that I have computed a solution, how do I determine which point is which? To this extent, you might use something which is domain dependent, or in case you have correspondences given externally, like you could use the error, the chi-square of that correspondence, to figure out whether it is an inlier or not. Or in case you don't have these correspondences at all, you could use some nearest neighbor, and then you match with the closest nearest neighbor, you calculate the distance, and if the distance is too large, you say, okay, this is no inlier. As I mentioned before, normally in this in this registration schema, people tend to use the appearance of some feature or some point. You can think, for those that didn't have computer vision, I recall you can think about the appearance as a characteristic of a point in the scene that is not captured, that it doesn't depend from it too much from the position of that point. Okay. The correspondence search typically uses the appearance, and these algorithms and the combination of correspondence search and detector extraction is characterized by an inlier ratio, which is how likely it is that for a typical pair of scenes the correspondences are correct. Typical inlier ratio are 0.2, and that's already a good inlier ratio. So So typically you get 20% of correct correspondences. In the example that we will do now, we assume these numbers. We assume the worst possible situations, that we have n times n correspondences and we have 1 over n as inlier ratio. This is the case of our ICP, but which is also the the easiest possible solution, because it doesn't require in our point registration system to have any specific technique. Basically, you have 2 point clouds and you say all correspondences, the correspondences are each point with each other point. So you have n times n or n times m correspondences. And then accordingly, given that only one will be correct, the inlier ratio is 1 over n. Because you have n squared divided by n. Okay? Now, if I give you 3 correspondences and I give you ICP, you could immediately think about a solver that does not depend on the initial guess, and the solver in this case will be using linear relaxation. And here there is a small recap of linear relaxation. Here there is a FIXMI, but I think I fixed it, and if not, I have to look back in the slide and copy them appropriately. But in this case, it makes sense to use linear relaxation to determine the correspondence. So I give you 2 point clouds, you don't know which one is which, and then you want to solve this registration, and I tell you register them. And you want to resolve the registration problem by using RANSAC. You need the ingredients that we have seen before: a procedure to shoot correspondences and the procedure potentially to select correspondences. The procedure to shoot correspondences is non-existing, which means that you have a match of each point with each other possible point in the other cloud, and accordingly, given only one point will be right, you have an inlier ratio of at most 1 over n, where n is the number of points. But the first ingredient is fixed, is there. Second ingredient is a solver which is immune to the initial guess, and to this extent we choose linear relaxation, that we know that converges with no iterations if the correspondences given are fine. Of course, in this case, the correspondences given will not be fine in general, and so we might drop many solutions. If you remember, the sigma or S value, the value of the matrix of the singular values, will be typically far from the identity if these 3 points do not register well. As I mentioned before feeding RANSAC, we might want to have a correspondence pruning strategy, something that kicks away in the generation phase, that produces a minimal set of correspondences that is most feasible than just a random one. In our case, just pops up to my mind that given these 2 clouds, I would just select 3 points in the one cloud whose configuration, so whose relative distances, are similar to the relative distances of the 3 corresponding points that I've selected in the other cloud. This is quite smart in a sense that already in the generation phase, I do not generate correspondence, or I do not generate triplets of points in the 2 clouds which have absolutely nothing to do with each other. Now imagine that in one cloud I sample 3 points that are 3 points that are this large. In the other cloud I sample 3 points that are that large. There's no way of matching these 2, and SVD will reveal it to me. So instead of doing so, I just do it before taking these correspondences and passing them to the minimal solver. To select the inliers, well, I recall that in this example of 3D point registration, we have n square correspondences, so you have all with all. The best that you can get in terms of inliers, if you look at the correspondences, is 1 over n, because if you find a perfect solution, well, you will still have the n square minus n correspondences which are wrong, right? But still, by using this, the error, the chi-square of a point, of a correspondence, you could figure out whether under the current solution it's an inlier or not. Personally, I would prefer in this case to do something different. I would preload the points in a quick search data structure, and then once I find the registration, I would call a point an inlier if there is another point nearby in the other cloud. In this way, I get rid basically of the identity of points. But still, in a standard computer vision setting, you just have correspondences which are given by your feature descriptor, and a classical strategy is to consider the chi-square error between the point and the projected point. And this allows you to answer a predicate: is given this solution, are these 2 points, is this correspondence a good one or not? If it is good, we can count it as an inlier. Okay? Okay, then basically we have implemented one iteration of RANSAC. So let's look how it will work. At my system will be fed, my system will be fed with a set of correspondences with 2 clouds. Then given these 2 clouds, I just generate all possible correspondences, so each point with each other. And this is the instance of my problem. Then for one RANSAC iteration, I pick 3 correspondences in the left cloud, 3 points in the left cloud, and 3 points in the other cloud, given that I know that each point might correspond with each other. And I pick these 3 points in a way that they form a triangle. They form 2 triangles which have the same sides. Okay, there's similar sides. Once I have done that, I can run my one-shot solver that will register these 2 triplets of points, but automatically it will carry behind all the 2 clouds, and so I will have to put the 2 clouds close to each other. At this point I have to say, hey, how good is this initial set? In order to figure that, I just look how close are the points of the remaining part of the cloud, by looking, for instance, at the residual chi-square error. Then I count the number of inliers, and if this number of inliers is higher than the number of inliers that I have found at the previous iteration, at the previous solution, because I have to repeat this process many times, I take this solution and I try another one. At the end of n rounds, I will have the best possible solution with that rounds. And what do I do with that? Well, this solution automatically identifies the inliers, and I can run the standard solver to run the final registration. A question that pops naturally at this point is, how many rounds do I have to run RANSAC for? Clearly it's a probabilistic algorithm, so how many rounds for what? Right? How many rounds? I would say infinite rounds, just the default solution. But we can only, because you're not guaranteed being it random. If you have outliers, you might be so unlucky that each time you sample some bad set of correspondences. But when there is luck and unluck, we can talk about probabilities. And so we can ask, what is the probability of having a correct solution after X rounds? To calculate this probability, we need to know clearly the characteristics of the problem. And the only countable parts, this algorithm is controlled, or the behavior of one iteration is controlled by 2 things. By the inlier ratio, so how likely is it that one of my correspondences is correct, and the other aspect of the algorithm is how many points do I need to compute the initial solution. And what I want to answer is how likely is it that after n rounds on this particular problem, I will have the correct solution. In order to find the correct solution, clearly, I need to find a minimal set of correspondences that are true, that are correct. Now, to answer this question, we play with probabilities. So defining W, my inlier ratio, n, the minimum number of model points, which is basically the dimension of the minimal solver. So in case of our ICP, this number will be 3. In case of we want to use the 8 point, this number will be 8. And then the other variable that I want to impose to answer, because my question is like, how likely is it? How many rounds do I need to have a certain probability of success? Is I have to impose the probability of success that I have to impose. So I could answer the question, how many rounds do I need in order to achieve probability of success 0.99? So the probability of fetching n inliers. So fetching n inliers, W is the inlier ratio. The probability of fetching n inliers is W to the n, because they are each time I draw independently. Okay, so if I have 3 points, this will be W to the 3. If I have 8 points, this will be W to the 8, right? So it will be, in our case, 0.2 to the 3, or 0.2 to the power of 8, right? Which is a rather small number. Rather small number that increases exponentially with the number of minimum number of model points. So with the size of our solver. Accordingly, if this is the probability of fetching n inliers, 1 minus W to the power of n will be the probability of not fetching n inliers. Okay? And this is just for one round. So at one round, I fetch n inliers. They will be correct with probability W to the n. They will be wrong with probability 1 minus W to the n. If I repeat, each round is independent, right? So if I repeat this game for n rounds, given that each round is independent, the probability of not having n inliers in k rounds is equal to the probability of not having n inliers in one round to the power of k. Okay. And then, in order to find k, we will equate the probability of failure, which is 1 minus p, being p the probability of success, to the probability of not fetching n inliers after k rounds. After doing that, well, we resolve by k. So we take the logarithm on both sides, and then we bring this object here on the bottom, and we get this formula over here. Now, the dimension of the model points is heavily controlling the algorithm, because basically 0.2 to the power of 3, you can count how much it is. 0.2 to the power of 8 is much less. Accordingly, this number here is much higher. And then, well, basically this denominator here will grow with the size of model points. You know, that's a log, right? So the denominator will be closer to 0 when the number of when n is when n increases, because log of 1 is 0. Okay? Because if this goes to infinity, this is smaller than 1, then log of 1 is 0. Okay? And that's the game. And this motivates basically the reason of finding effective minimal solvers. And this explains why in computer vision there has been a lot of research in finding algorithms that are able to register two images with a minimal set of correspondences, which is 5, instead of using the much easier 8-point algorithm, because 2 to the 5 is much smaller than 2 to the 8. And accordingly, if I have a dirty system that provides me wrong correspondences, I will need much less trials. Okay? And that's RANSAC. If you have questions, write them in the chat. If you don't have questions, I proceed with the second part of the lesson. But I don't see the chat. Anyone can write. I don't see anything in the chat. Okay. After talking about RANSAC, which is a schema, it's not an algorithm, we can talk about multi-point registration. So to this extent, we will lift our ICP to more than 2 robots. We will have n robots, or maybe a sensor in the environment that is moved in the environment, right? So each time the sensor is moved, for us is a new sensor, so to say. Doesn't change much in this setting because we want to estimate something static. Okay. So the game is as follows: we have a certain number of identifiable still landmarks, but now we might have also guessed how to solve the problem, or how to approach the problem in case of wrong correspondences. But at the beginning, in this problem, we assume them to be identifiable. So we have a scene consisting of a set of 3D points, and this set of 3D points are seen by a device which is capable of revealing their relative transformation, their relative position with respect to its own reference frame. And what we want to do is we want to determine both the location of the landmarks, right, and the location of the robot positions. Like in contrast to the traditional ICP problem, where one of the elements is the fixed points in the scene and the other ones is the points in the sensor. So part of the points are fixed; they were constant. In this case, every point becomes also a variable to be estimated. So the input of our problem consists of a set of sensor to point measurements and nothing else, or maybe the initial guess, because we are still in a least square set. Okay, and what we want to determine is therefore the location of these landmarks and the location of the robot position. Okay, which we're getting closer to SLAM, right? Now, given this problem, we will rigidly follow the methodology that for least squares that we have been using so far. The methodology tells, first of all, define the state of the problem. Now, in this case, the state of the problem is a thing, a data structure, representing a collection of the transforms, because each device, each sensor, has a position in the 3D space that we want to estimate. But our state, which I repeat is a data structure in this phase, contains also all the 3D points that we do not know where they are because they are being estimated. So our state will be consisting of n elements of SE3, one for each robot position, one for each sensor or robot position, and m 3D points belonging to R3, representing the landmarks in my scene. Are there questions on that? Is that clear? So this is a listicle problem. I'm asking you, you have endpoints observed by endpoints observed by n cameras. Find me the minimum norm solution. The state is the points and the landmarks. So the landmarks and the robot position, the points or landmarks. The state. But the state is a complicated object in this case. And so it's not anymore this nice SE3 object. Okay, it was just a matrix. It's a collection of things. How to represent it in your program is your business. Okay? Just you have to store these variables, these values. How I would represent it by using a proper, even by using Octave, let's say, you could represent the state by a compound, two things. First, a vector of rotation matrices, which will be a 3D vector, right? And then a matrix, a 3 by m matrix of points. And these two objects here will hold the representation of your state. Then the question is, what are the increments? Well, the increments, the first answer is like the increments should be large enough that can express a perturbation of every element, a valid perturbation of every element of my state. So, given that I have m robot positions, for perturbating each of these positions I will need a 6D vector, because this is a 3D robot position. And for perturbating a landmark I will need a 3D vector. So the answer is the dimension of the perturbation will be a large vector consisting of 6n plus 3m elements, which are actually, very reasonably, all the perturbations, the individual perturbation vector applied to each single variable of the state. So I will have a perturbation of dimension 6 for this variable, plus another perturbation dimension 6 for this, 6 for this, 3 for this that represents a landmark, and then finally also 3 for this that represents the other landmark. Okay? And then, well, in this way we could somehow reuse or extend the definition of box plus that we have already introduced in the context of the manifold and 3D registration problems. In particular, we will see it in the next slide. Okay, if I want to implement the state on Octave, because this lesson goes pairwise with Octave, like goes together with the code, I will represent this state here, with an array of 4x4 transformation matrices for the robot positions that becomes a 3-dimensional matrix in Octave, and a matrix 3 times the num landmarks for the element for my landmarks in the map, for the points being estimated. Okay. Okay. Having introduced this representation of the box plus and of the state, from a purely programmatic point of view, it comes in rather handy to have functions that, given a variable, like for instance the first robot pose or the third landmark, are capable to identify the index within the perturbation vector from where the perturbation of that variable starts. Just to make you an example, let's say that I want to calculate programmatically, I want to figure out what is the index of the first variable of the block that applies the perturbation to the first landmark. Well, this index here will be equal to the number of poses multiplied by 6, no? Because this way I'm moving 6 times, so n times 6 times at each step along this vector, and then considering that I am on octave and the vectors start from 1 plus 1, okay, and I will find the first element of my the first landmark. Similarly, so accordingly, in order to calculate where this vector here, where this perturbation here begins, I need to know how many poses I have and what is the index of the landmark that I'm picking up. Because if I would be picking up, for instance, the second landmark, well, then in this case I will have to go ahead n times n times 6 times, and then I've eaten all the landmarks, plus I have to go ahead 1 time to skip the first landmark, and then times 3, because these blocks are big 3, and then I will find the where the index of the landmark number 2 begins. Okay, so it's annoying bookkeeping. If you use different programming languages, you don't need to do this, right? Because you don't need to encode everything in a vector. So, but we will need them in crafting this program. So, how do we determine the index of a robot position? Well, let's say that this is the third robot pose. The third robot pose will be at 1 plus number of pose index minus 1, because I have to subtract 1 because I'm on octave, times 6, and I find the position of where the perturbation of the pose index variable begins. Similarly, for the landmark, I will have to skip all the poses and then move forward for the number of landmarks. And then just for completeness, you have here the octave implementation of these two functions that I hope will not generate any pain in the belly. There is also some useless check to see if you do something bad, like if you try to access a pose index which is after the maximum boundary. The first function, pose matrix index, takes the pose index, takes the number of poses, takes the number of landmarks, even if it's unused, it's only for symmetry with the other one, and then it calculates the index of the first of the pose having index, pose index in the perturbation vector. And this one does the same for the landmarks. Okay? Now, so far we are only able, we have done two things. We have, by applying the methodology, we have defined the state space of our problem. We have defined the perturbation vector. And then also we have introduced two useless bookkeeping functions, that useless from the mathematical point of view, but useful programmatically, that allow us to retrieve the indices of an element within the perturbation vector, which I repeat as the dimension sufficient to move all variables in the state. Now, given this perturbation vector, I have to invent a box plus operator. I could do anything I want, but it makes pretty much sense to extend the definition of the box plus used for the SE3. So basically saying that given my state, so this huge data structure which contains all the matrices, all the transformation matrices and all the landmark vectors, and given a perturbation vector that is also a quite large thing, it applies this perturbation vector to this data structure, and it returns me another data structure, or maybe the same doing side effect, but another data structure that is obtained from the previous one by applying the individual perturbation to each element, to each corresponding element. Is that clear? So in order to define the box plus that now operates on a large state and takes a large perturbation vector, we unpack the perturbation vector and the state in little components, and we apply the box plus that we know to every individual component. Accordingly, the box plus defined in this domain will be for each pose. If the pose is a robot pose, I will take the perturbation, Why on the right? Well, this is should go on the other side. There is a mistake in this line. But anyway, I take the robot position and I compound it with the perturbation using the classical V2T that we have seen a million times so far. And I do the same for the landmark, only for the landmark, being the landmark an Euclidean measurement, it's a vector tree, I just sum it up. Is that clear? Yes or no? Okay. Okay, so having described how to calculate the box plus, we see how to program it. So the box plus will be a function that takes our state that in Octave is represented by these matrices organized in an array, XR, robot position, and XL is are the landmark position, and takes the indices of our, or the dimensions of our problem, non-poses and non-landmarks. Albeit those two could be retrieved directly from XR and XL, because this will be just the dimension, the number of matrices that I have stacked there. This will be non-poses, and this will be just the number of landmarks that I have in my landmark data structure. And then, of course, I need the dx, which is a perturbation vector that I recall will be this large object which is 6m plus 3n. Let's see, n. Yes, 6n plus 3n. Okay. Very good. Now, to calculate the box plus, following our specification, for each pose in my data structure, I calculate the index of the pose by using into the perturbation vector, and by using the function pose matrix index that I've defined before, so I know where my delta XR begins. I extract the perturbation vector for the pose, which is a 6D vector, so like that starts from pose matrix index and goes to pose matrix index plus pose dim, because pose dim is we made it parametric. This is 6 in our domain, so take 6, a portion 6 of this vector. We take the rotation matrix, which is in location pose index, which is the index of the position, and then we apply our box plus operator as we do all the times to this particular element. And we will be doing the very same for the landmarks, only that the box plus degenerates on a standard plus. This is basically the implementation of these formulas here with this one here that should be blasted away. Like, should be flipped. So XR box plus delta XR. There's a little evil that changes the slide somewhere. Maybe me, but who knows. Okay. We're done with the state, right? So the methodology says qualify the domains, done. Define the perturbation vector, done. And the last thing, define a way on how to apply the perturbation vector to your state data structure. Oh, observe that our definition of box plus is consistent with the definition of, with the requirement, because if my perturbation vector is 0, well, the state doesn't move from where it was before. Okay? Now, we have defined the state, and it's time to take care of the measurements. Now, in this problem, a measurement is characterized not just by one index, but let's be more gentle, and let's put the measurements, attach two indices to the measurement. Given that one measurement in our problem is one observation of a landmark, this is our measurement. But which landmark and which robot positions? So we say the nth robot position and the nth landmark. Okay, and the one of these observations, 1, is therefore characterized by two indices, the observing robot position and the observed landmark. Being a 3D observation, but you could also write a posit version for that, like a projective version for that, but in this case we're focusing just on 3D fully qualified observations. One of these observations will be a 3D vector, or x, y, z. This is a z. Okay, I'm noting the typos to fix. Okay, x, y, z, and what will be the prediction? Okay, the prediction is a function of the state. So the prediction is the prediction of the observation of the nth landmark by the nth landmark. All indices are wrong. Nth landmark from the nth robot. Okay, quite simple. We have seen it in ICP. Assuming that the landmark is in that location and the robot is in that location, or the position of the word with respect to the robot, as we always do. How to express the position of the landmark in the robot reference frame? Well, we take the position of the word with respect to the robot, this is XR here, and we multiply it, being it a transform it holds, and we multiply by the landmark position in the reference frame of the word. And this returns me the position of the landmark in the reference frame of the robot, which is actually the prediction I want to have to solve this problem. Observe that my prediction function, to be consistent with the least squares, takes the entire state, so the entire data structure, even if in the end it only uses two little parts of it. But just to be compliant with least squares, I write it in this way. Then clearly X contains XR and XL. So there's no harm here. The measurement vector is Euclidean. So being Euclidean, this means that the error vector will be equal to the prediction minus the measurement. Similarly, once we want to write down the error at the perturbation, we observe that since the prediction of the point, the landmark M with respect to the robot pose N, only depends on the location of the robot and the location of the landmark, also when we write it at the perturbation, we will find that all other components of delta x are not appearing, because if I perturbate another robot position, this doesn't have any effect to the observation of a landmark that I'm doing from this robot position. And this is the expansion of the application of the box plus over delta x to both variables that are involved in the measurement. In particular, this is the box plus over the robot position, and this is the box plus over the landmark position. To understand why it is like that, just like replace the box plus, just look back the definition of box plus. Okay, this is the box plus over XR, and this is the box plus over XL. Well, I'm almost done here. I've defined the state, I've defined the measurement, I've defined the prediction function, and I've also defined the measurement function. And everything fits into the least square machinery to the manifolds. Now, the bad part, calculating the Jacobians. The very first question is, how large will be my Jacobian? And I will stop until someone doesn't write the answer, and I will also change slide, otherwise we look at it. How big will be the Jacobian of this quantity over here? I go to get a glass of water in diretta while you write something. Hopefully someone will tell me how big is the Jacobian of this error function. No one. No one. Okay, I will ask another question. How tall is one measurement? What is the dimension of the state? Oh, yes. This is the dimension of my Jacobian. Exactly. So the dimension of the perturbation. Yes. Exactly. Therefore, my Jacobian will be a thin and large matrix, like this one. Additionally, I observe, being the Jacobian defined as the derivative of the error function with respect to the perturbation, and observing that within this the equation of the error function, only the perturbation with respect to the nth robot pose and the nth landmark appear, we could observe that this Jacobian matrix will be zero almost everywhere, because the derivative of a function with respect to a variable that doesn't appear in a function, it's zero, it's a constant. And it will be characterized by a block structure, because if you observe our perturbation vector, which is basically lying on top of the Jacobian, just to give it names, the first block 3 by 6 will be the derivative with respect to delta XR. Then the second block 3 by 6 will be the derivative with respect to delta XR2, and so on, right? And these blocks here will be tall 3, yes, and large as the perturbation on a landmark, so 3. And this is what we find here. So in general, our error will be, the derivative of our error will be 0 everywhere, but in two tiny little parts. And these tiny little parts correspond to the derivative of the error function with respect to the robot position, or the perturbation on the robot position, and the derivative of the error function with respect to the perturbation of the landmark. Okay? Similarly, we could write down our prediction as it is, and we write this prediction as z hat mn, which is equal to the robot position. When I say robot position, there's a hidden understanding here that I'm talking about the position of the word with respect to the robot. Otherwise, this formula would be wrong. I would need an inverse here. So my prediction is equal to the robot position and multiplied by the landmark position. Okay? And I have the landmark in the reference frame of the robot, which is what I should observe. Now, the derivative of this function, or the derivative of this function over here, look at it. Derived with respect to delta XR and evaluated in delta XR equals to 0 and delta XL equal to 0 should sound quite somehow familiar, isn't it? If here I wouldn't have delta XL, which I don't because it's a constant in this case, and it's because it's equal to 0, this function here would be the Jacobian of ICP. Am I right? Because this is the error function of ICP. If I compute the derivative with respect to delta XR. Exactly, so this will be the Jacobian of ICP if I derive with respect to delta XR. In contrast, if I derive with respect to delta XL, it will be something slightly different. But luckily, when I derive with respect to delta XL, this component here evaluates to the identity, because I have to evaluate v2t in 0, which returns the identity and doesn't incur in the derivation. And so I will find something interesting on this side. In particular, if you do the calculations, and I invite you to do it, the derivative of the error function of the projection of the mapping of a landmark in the robot position with respect to the robot position is obviously the Jacobian of ICP. Therefore, we put here z and n. This z hat and n takes the role of the p prime in the derivation of ICP. Now, to understand, and this block here, that is 3 by 3, will be equal to the rotation matrix that we call Rn, why Rn? Now, go back and delete this part from the equation, because it's evaluated in 0, and expand the product, so you will have XR times XL plus XR times delta XL, right? If you derive this equation over here, you will have two terms, XR times XL, which doesn't derive the remaining part with respect to delta XL. You will have, therefore, two terms, XR times XL, which doesn't depend on XL, and so derived makes 0. And then the second term is XR times delta XL, which develops in the rotation matrix of XR times delta XL plus the translation matrix of delta XR, of XR. But the translation matrix, the translation vector. But the translation vector is a constant, therefore the Jacobian of this object calculated with respect to delta XL is just the rotation matrix of this object over here. And therefore, we find the rotation matrix here. For simplicity, let's call in the remaining part of the lesson this block here JR, which is consistently 3 by 6, and this block here JL, which is consistently 3 by 3. Okay. And so we implement the difficult part of this exercise, which was error and Jacobian. In this case, before we had just one Jacobian, in the previous exercises, here I find it handy, instead of returning a huge matrix full of zeros, I find it handy to return two little blocks, one for the rotated robot part and one for the landmark part, which will be 3 by 6 and 3 by 3. And this is just the implementation. Extra rotation matrix, extra translation vector, compute the prediction, compute the error, construct the robot Jacobian, and construct the landmark Jacobian. Where these are the arguments, clearly. And also here the state is unpacked. Now, we might also observe that in the calculation of one iteration of ICP, and this will be a dominant part, and this is why not taking advantage of the special structure of H will lead to poor performances. But being the Jacobian sparse, we might expect, so with many zeros, we might expect that also the H matrix and the B vector for one measurement will be sparse. Because if I do the product J transposed omega J to calculate H, and if I do the product J transposed omega E to calculate B, I will find the following structure, because everything else is 0. Remember that J is consisting of many zeros, JR, many zeros, JL, and many zeros again. Once you do the products, then you get this the following structure, where you will have only 4 non-zero blocks. One corresponding to the robot contribution, one corresponding to the robot landmark contribution, one to the landmark, and this is the transpose of this. Similar for the B vector. Well, this is even easier to see, because if you consider that the Jacobian has only 2 dirty blocks, once you multiply it by an omega and a vector which are dense, you will find in output the same structure of J, the same fill-in of the rows of J in B. To do this, exploit our findings, we need to think a little bit how the compilers work. I mean, the compilers, when you write an expression like A equals A plus B, a naive compiler or interpreter will evaluate the right-hand expression after the equal. So it will create on the stack a temporary for the result, where it will put H or A, and then it will sum to this AB. Then this object will be living in the stack, then it will be returned up when the function closes, and then it will be copied back to the leading destination. Of course, if you enable optimizations, something smarter could happen. But it's quite a silly idea to calculate the entire H matrix, which has 6n plus, so the 6n plus 3n to the square elements, where this n can be also potentially large, like in the order, like classical problems might span up to 1 million of landmarks, okay? Not classical, but large problems might have 1 million of landmarks. So you don't operate on a matrix which is 1 million by 1 million, especially if you know it's sparse. It's like doing this operation of calculating a temporary, putting it in the stack, bringing it back, it's completely useless, considering what we want to do within least squares to our H matrix and our B vector. We would like to have a large canvas that contains H, and each time we add a contribution, we would like only to copy the contribution with a plus equal operator, which modifies the destination, like in the blocks that we are going to modify. Okay? This is a much smarter option. And this is actually what is done in this simplistic implementation over here, even if it's... do you see anything? Well, it's small, but if I don't move the mouse, I think the encoder will kick in. We have a... and this is the classical loop for one iteration of our algorithm. We create a matrix and a system matrix and a B vector. We populate it, we fill it with 0. For all the measurements, basically we extract the measurement from our measurement set. We extract the robot position, we extract the landmark position from the state that correspond to the indices encoded in the association vector, and then in this way we have the blocks we need to modify. We calculate the error and the Jacobian that will return us JR and JL, and of course the error for this one measurement, and then we can compute the contribution of the H matrix and the contribution of the B vector that I recall. This is one robot landmark, landmark. This is the transpose of this. And for the B vector, I will have robot contribution, landmark contribution. Everything else is 0. So it makes quite sense to operate on small 6x6 or 3x6 or 3x3 or 3x6 matrices, which are HRR, HRL, HLL, BR, BL. Okay? Once we have these contributions, then we can update our system matrix, and we do it in an additive way without taking the whole H and constructing a delta H contribution and H of the measurement contribution, which is another large matrix, and summing the two. We could just retrieve the block that corresponds to the robot position and sum to it with a plus equal operator the contribution of the H matrix which belongs to it. And the same we can do for the robot landmark contribution. The same we do for the landmark contribution. If you look carefully, you will see here that the indices are respecting basically the bookkeeping that we have defined at the beginning. Therefore, we needed this post to landmark to landmark index. Otherwise, we get crazy with the indices. Similarly, we can do the accumulation in B. Okay, and then we are done. But we're not ready yet, because we will find, if we run the system, you will figure out that Octave tells you, oh, this system is rank deficient, this system is rank deficient. When Octave encounters a rank deficient system, what it does is that it computes SVD, so which takes ages on a large matrix, and then it returns you the solution with the A solution with SVD by enforcing the NOR to 1. And because it's otherwise the system is underdetermined. But the question is like, why is this system underdetermined? And now I'm waiting, well, it's written in the slide. It's underdetermined because if you calculate the perfect solution that explains with 0 error all the measurements, so all the robot landmark observations are perfectly matched by the landmark positions that you have estimated and the robot positions that you have estimated. So you have a 0 chi-square error. But given that the measurements are relative and we are evaluating the robot positions and the landmark position in the world, you could find another solution just by applying a relative transform to the solution you have just found. And given that you moved rigidly everything, well, the error will still be 0. And how many degrees of freedom you have? Well, how many degrees, in how many ways you can transform the solution in a way that the chi-square doesn't change? In 6 ways. You can the 3 translations and the 3 rotations. So the system will not be solved because it's underdetermined. And it's underdetermined because the problem is underdetermined. So there are 2 ways of making the problem, being able to solve this problem. The first one is to force some variable to be locked in the origin, the first thing. And the second option is to add to this problem another measurement or another constraint that we call prior, that will force one of the variable to stay in a location that we want it to be, where we want it to be. So defining an origin, basically. Now, the solution I typically prefer is to eliminate the variables. Now, if I give you a linear system, and I tell you, hey, look, man, in this linear system, one of the variables has to be 0. What can you do? You could simply set to 0 this variable in the linear system and move the coefficient on the other side. The corresponding coefficient, or basically deleting the coefficients of all that part, because this will result in setting them to 0. Okay? Now, if you have a linear system with x1, x2, x3, xn as unknowns and a matrix n by n as the coefficient matrix, and a b as a vector, then in case you want to eliminate a variable because you know the value, you could straightforwardly set the value of the variable, substitute in the coefficient matrix, and then in this case, if it is 0, you don't even have to substitute, you can just delete the column, and then you take this contribution back to the right-hand side. This is straightforward. And this is actually like what I like the most in general, because it reduces the system and there's no way. Doing so in our problem results in basically setting delta x of one of the positions while we are solving our linear system, setting the perturbation of one of the positions while we're solving the linear system to 0. So we say this perturbation here has to be 0. If the perturbation has to be 0, this means that the variable to which this perturbation is attached will not move, which means that we block the variable. How to do this? Well, we simply suppress the rows and the columns of the variable, or the variables, in case they are more. In case we want to block multiple positions, we can just eliminate, because maybe we have the ground truth, we could eliminate the variables that we know that they stay fixed. Of course, we have to preload the variables with some good value, otherwise we will lock them to a wrong position. And finally, we solve the reduced system, which is the linear system to which we eliminated the columns and the rows of the variables that we want to kick out. After we do this, of course, we obtain a perturbation vector that will not include the perturbation for the variables that we have calculated, we have suppressed, but we are smart and we apply the perturbation only to the variables that actually are active in the system. And this is how to implement it in Octave. So, perturbation vector, system size is the 6n plus 3n. Perturbation vector. And then, in order to solve the system, we consider a perturbation vector that starts at post-dim, basically. So we skip the first elements, and we use the backslash operator in Octave on a reduced matrix that comprises, that suppresses the first 6 rows and the first 6 columns of the H matrix. And clearly we have to do the same for the B vector. Once we have done that, we take the dx, to which the first 6 elements were 0, and we apply the entire box plus to our machinery, just because we are lazy. Okay, this is the solution number 1. Solution number 2. When to use the solution number 1? Well, if you have only one undetermined degree of freedom in your system, like only this, you don't know where it starts, well, this is the preferred way. Because you don't know where it starts, there's no way, it's not that you have a prior, you really don't know. And if you don't know it, it's much better that you say, I perfectly know that I started in the origin. Second solution, adding a prior. When to use this second solution? A prior is a constraint, but it's a soft constraint. That you could see it as if it was a GPS. That tells you, okay, you are here, but it's not that you are here with 100% probability. You are here with a certain, probability. Actually, GPS gives you only the translation. You need also the heading. GPS with a super accurate compass business. Okay, that would be a prior in this problem. And you might also receive multiple GPS measurements along your way. And you could enforce, each time you receive a GPS measurement in a location, you could attach this prior, this measurement, that depends only on one variable, which is the robot position at which you receive the measurement, in the point where you receive it. How to implement a prior? Well, we could add an error term, which we define to be delta XR, just a perturbation in our case, to make it simpler. We might add the Jacobian, having defined the error of a prior. Observe how the error of the prior is defined. The error of a prior of a robot position, of course, box plus, no? E of delta x, of x box plus delta x, in this game I just defined it to be delta XR. Just defined it to be the perturbation. Because I'm adding a prior which is very lousy. I don't care where the robot is. I just don't want it to move too far. And I want just to add some constraint to the system so that it's determined. What I'm simply saying is that I want the perturbation on delta XR to be as small as possible, ideally 0. Being the system underdetermined, I will always find the perturbation delta XR equal to 0. The derivative of this function with respect to delta XR is I, right? And I could define an omega of the prior, like being j omega j, the H matrix, the prior of H will be omega prior, because the Jacobian is the identity. If I multiply the prior to the left and to the right by the identity, I'm fine. And equally, the B of the prior will be 0. Remember that this prior constraint has to be composed together with all other constraints that I have in my least squares. But this is easy because, and this comes naturally, because you might observe that the error of the prior in theory is defined over the entire state vector, only that it's active only in delta XR, in the variable that you want to eliminate. Now you could also think about implementing a prior that constrains the robot position to certain measurement z, and in which case you would just like take x, which is your measurement, like x, which is your robot position, and you would use an error function, which is the estimated position, like the GPS position, and you will box minus to the actual robot position, right? Because if you do so, this error is 0 when the prediction and the measurement overlap, and then you have to do the maths for that. The cool thing is that you can add any prior as you want. This version over here that I introduced you serves only to get rid of the underdeterminacy of the system. How to implement it? This is the other option. You take clearly, if omega is 0, it's like you had no prior to your system. The larger the omega, the more stiff the constraint, and the more your system will be stay fixed. Normally, if you want to block the system by using this technique, you add a large value to the variable that you want to block. Okay, and then you solve the system. Now, some consideration that it's important, and we will recap the next time, is about the running structure of H while we construct this linear system. Now, let's imagine that we have a Jacobian that is correlating, this is the robot position and this is the landmark position, okay? During the evolution of my system, during one iteration, I will progressively augment my B vector, the total B vector, by adding first, for instance, a measurement between this robot position and this landmark, then this robot position and this landmark, and so on, right? Given that at the end of the game I will have involved all landmarks and robot positions, because otherwise something is not observable and I kick it away from the state. If you put together all these contributions, this reddish here denotes that the block is full, you will end up with a B vector which is full of elements. In contrast, the H matrix has a little bit less elements, and if you observe what happens to the contribution of one measurement to the H matrix, and I'm always talking about a measurement between a robot position and the landmark position, robot position, landmark position, so this is j omega j, you will have 4 blocks. In particular, you will have a block which is in the position which is corresponding to robot, a block which is in the position that corresponds to robot landmark, and you will also have a block in the position that landmark, and you will also have a block in a position that corresponds to robot landmark. Okay. Well, if you add then another matrix, another contribution, you will find elements on the diagonal and an element, one single element in the part that corresponds to robot landmark position. So at the end of the game, we might imagine that all the blocks on the diagonal will be full because all variables in the end appear. Otherwise, they are not present in the problem we want to optimize. But each single measurement will give us a contribution on only just one single block. And on which block will it be giving our contribution? Well, on the block that corresponds to the intersect between row and columns of the observed robot and observing robot and observed landmark. So if we would represent the problem as a graph where each node represents a variable in our problem, so either a landmark position, a robot position, or a landmark position, and each edge represents an observation, a measurement done by a robot position to about a landmark position, so an edge, then the structure of the H matrix reflects the I don't know, it's called it's not the incident matrix. The structure of this is the structure of this matrix reflects the structure of the graph. This is the matrix representation of the graph of the measurements. And in particular, you might find that here you will have a number of non-zero blocks, excluding the diagonal, which is proportional to, which is at most equal to the number of measurements. Now, if you consider that in a classical SLAM problem, you have a number of measurements which are growing linearly with the number of positions. And more or less at every round you observe the same amount of things. So you will have a constant amount of measurements for every robot position, right? Turns out that for each robot position you throw in, you add a proportional number of measurements, okay? But the number of elements in H, so you grow linearly. The number of blocks grow linearly with the trajectory of the robot. But the number of elements in H grow quadratically with the trajectory of the robot. Which means that sooner or later, your matrix will result in having a lot of non-zeros, because if the one end I'm adding elements linearly, but the amount of space that I can write in grows quadratically, well, sooner or later, or more sooner than later, the structure will be sparse. And this consideration of the sparsity of H is at the key of modern SLAM system. Okay, and this is the reason why normally why we can deal with very, very large problems, because we exploit the sparsity of H. Now, to conclude this this problem, or this pack of slides, I will run the code, and then Tiziano, if you are alive, can you turn on a Zoom while I show them the code? Thanks. Okay. How to see this thing? Yes, adjacency matrix, that one. Of course, you have your the program that I've illustrated you is available in its beauty. Okay, so I will never need it again. Generation of the data set, we set 100 landmarks, 5 robot positions, a word size of 10. We generate a certain number of landmarks in the word, in particular 100. We treat the positions coherently with the definition as an array of 4 by 4 homogeneous transforms, and we treat the landmarks as we populate the landmarks with the points in the word, because later on we will be modifying them. We put the first pose at the origin, and then we generate okay, we generate what I'm doing here, I think, is that I'm generating random positions by generating a random scale and applying this scale to the matrices. Here I'm just like constructing the problem, sampling positions. Okay. Then we construct the matrix of measurements, and we say that every pose observes every landmark, just for simplicity. Accordingly, the measurement vector will be equal to number of the landmarks times number of the measurements. This Z is a matrix for consistency, and we will also have a matrix which we call association matrix. That is a matrix of which is large as the number of number of columns equal to the number of measurements, and it has 2 rows to encode the indices m and n that correspond to the corresponding column of the measurement vector. So that we can keep the bookkeeping between what is what, right? And we can generalize, you render this program, which is a little bit more flexible. Okay, so then the next, what we do, we generate the measurements, right? So like we fill in our measurement vector by, for each pose and for each landmark, we throw in something in the association vector to produce the measurement, the predicted measurement, okay? And we apply a perturbation to this measurement with a certain noise. Okay. Finally, we also apply a perturbation to each robot position, just to say that we do not start at the global optimum. Otherwise, everything would be easy. And this is what we do here. So we shuffle our things. And similarly, we also ruin our state by perturbating every landmark. So like we need to do this acting on the guess variable, because otherwise we would start at the optimum and there's no reason to conduct any sort of optimization. Then we run 10 wonderful iterations. I need to I put a little kernel, I think, I'm not sure, and a damping, and then we plot the state. Plotting the state, we just like plot the 2D projection of the landmark positions, even if we know that they will be represented in 3D. Yeah, but make it simple. The rest of the code was in the slide, so I'm not commenting it. Voila. What do we see here? The bad circles are the landmarks when we span them in the state. The green dots are the landmarks where they should be, and the red dots is the initial guess. Actually, I don't even know which landmark was which. I should plot lines, but if you have fun, you can do it. And well, this opens the new chapter that we will continue next time, another next time, on sparse least squares, which is the last but maybe most important part of the course. Now I go to Zoom to answer questions. Meanwhile, Tiziano, if you want to start answering questions, I'm up.